This morning, going to talk about a subject that I've been thinking about for some time, but I've been hesitant to give a talk on water, largely because I'm not a hydrologist, a person who studies water and water resources. I've never had a course in it, never done any research in that area. So it's an area that I don't have firsthand experience with. Yet, as I thought about it, I realized that basically every rock that I've worked on in my career has been influenced by water at the time it accumulated. And so water was really a big part of my background, even though I don't know very much and have had to learn a bit about the whole system of water resources, which I'm not going to be playing up a whole lot in this. I'm going to be looking more at the history of water on the planet, what it means, what it does today. Here's the outline of today's talk. We'll talk about the shape or shapes of water, water in the solar system, then water on Earth, and the origins of the Earth's water, the earliest oceans and plate tectonics, and then a catastrophic change that occurred and altered life on Earth forever. And then we'll talk about the salt of the oceans and sea level through the ages and today. Then we'll talk about water as a resource, as a scourge or a vital resource, a bit on the hydrologic cycle, something on floods and droughts, and then water here and now, our local reservoirs, and issues like subsidence and saltwater intrusion that impact our water supplies today. So that's the outline, a fair amount of stuff to cover. And we'll start with the shape or shapes of water. And water has a funny little molecule, kind of different from a lot of molecules because it has the two hydrogens are clumped on one side of the oxygen, which gives it a polarity, an electronic polarity, with the two positive charges being on one side and the negative side where the oxygen is. That's where the negative charge is. And this really is critical in a lot of ways in how water behaves, because first of all, this is how liquid water ties together. It's this linkage, this electronic bonding that allows water to stick together and not just fly all over the place, the liquid water. And so it's these hydrogen bonds that keep water as a liquid. If you break those, it becomes steam or gas. And so we have the three familiar states of water: the solid state, ice, where the molecules are completely lined up and locked into formation, and then liquid, where they're bonded together, but they can still move around. It's fluid. And then finally, where they're broken apart completely in water vapor or steam. But it turns out there are a whole bunch of, to me, unfamiliar states of water. These are polymorphs of ice. Polymorph is just different forms for the same material. And probably the classic example could be carbon, pure carbon. Forms graphite, which is black and greasy and so soft that if you pull a point of it across a piece of paper, it leaves a line. And yet there's another polymorph of carbon that is the hardest substance we know on the planet, diamond, brilliantly clear. Two very different kinds of forms of the same material. And so water has the same way. There are a whole bunch of, to me, unfamiliar states that were polymorphs of ice. They're talking about maybe 20 of these now, and one of them, ice 18, is a doozy. And this is one they've actually created in the laboratory using two diamonds, the points of two diamonds driven together to create an immense pressure, about 1.5 million pounds per square inch, and lasers to heat it up to about 5,000 degrees. And they had an X-ray diffractometer hooked up and verified that they'd formed a crystal of ice in a very different form, superionic ice, solid, black, and hot. It melts at about 4,700 degrees. And the oxygen atoms are fixed, so they don't go anywhere. They're the rigid part of this. But the hydrogen atoms can just move all around. It's a very, very strange form. And it's just one of a bunch of forms that are either theoretical or have been identified for ice in its different forms. So that takes us to the solar system. And those of you who are a certain age, like I am, were probably subjected to the rhyme of the Ancient Mariner. They had to read it when we were in the 8th grade. And the most familiar line, I'm sure, that came out of that book, the most memorable line is, "Water, water everywhere, nor any drop to drink." Now, this was the result of killing an albatross, but in the solar system, it could be applied here as well, because there is water a lot in the solar system, but it's not a drop to drink, with the notable exception of the Earth, our own planet. The gaseous planets Neptune and Uranus have anomalous magnetic fields that have puzzled astronomers for some time. And it has been postulated that these two giant icy planets have cores that are formed by the solid superionized ice 18, that sits around a rocky core, and that could explain the very peculiar magnetic properties of these two planets. And there is liquid water thought to be there, but it's buried well beneath the surface. There's nothing at the surface. Jupiter and Saturn are both giant planets that have a lot of moons. Jupiter has 69 of them, and one of them, Europa, is exceedingly bright. And it's thought that the reason it's so bright is the surface is ice. And several research groups have thought they have detected geysers on that surface. And these would be geysers of probably ice coming up from down well below the surface, but indicating a fair amount of water on that particular moon. Saturn has 53 moons that are confirmed, and another 29 that are awaiting confirmation of their discovery and official naming. And one of these, Enceladus, is a tiny little moon in the outer ring, and it's been found to have geysers on it. And these, apparently, the best explanation is there's an icy crust, and there are vents in it, and water spews out. It chills and forms ice at the surface. So these are ice geysers. So there's lots of water, but it's not liquid. It's all icy. Mars, big question was, had Mars at one point had liquid water? And there are clouds that were thought possibly to be water-bearing. They are not, but there is ice on the poles of Mars, and the surface has given indications that water did exist in a liquid form. And this past year, a paper was published in Science, and the minute I saw this particular photograph, this illustration, I knew that there had been standing water and rivers on Mars, because those inclined beds that are shown there at F sort of in the middle, are present on Earth, and they only form really in one way, and that is where you get a river depositing sediment into a lake or other quiet body of water where it just piles up as these great big sloping surfaces. And these are common in the geology of the Earth, but to find them on Mars meant that, I think without any question, Mars about 3.7 billion years ago did have liquid water on the surface. But Mars is only about a third of the size of the Earth, so its gravitational field is much weaker. And so it couldn't retain the hydrogen that's needed to form water. And the consequence is that it's basically lost most of its water and does not appear to have any liquid water on it today, in contrast to the Earth. So where did the water on the Earth come from? You'll notice I say origins because there may have been any number of ways that Earth got its water. It is a water planet. We have lots of surface water, but if you look at the actual volume of water that we have compared to the size of the Earth, it's not all that big. It's just spread around on the surface. So where did this water come from? This is a question that is still being debated. But the solar system formed probably 4.6 to 4.7 billion years ago, and in it, planet Earth came together. And as it came together, icy blocks would have brought ice in, but it would have been really pretty hot. Everything would have melted. There could have been much water incorporated into the interior part of the Earth. We just don't really know very much about what went on at this particular period of time. But not only did we have water forming from the Earth, but comets coming in are mostly water. And so their impact would add more water to our planet. It's been estimated that maybe a third or so of the ocean's water may have been brought to Earth before the sun was born. So some of it could be really, really old. And I guess the point is we don't, probably not a single origin for all of Earth's water, and it's got to be some mixture from a variety of sources and conceivably from other ones we haven't even thought about yet. Early in the Earth's history, it collided with a Mars-sized planet that blasted the Earth and created the moon. And after that collision, NASA estimates that the Earth's temperature atmosphere was about 3,600 degrees Fahrenheit. You're not going to get any liquid water under those conditions, but might have formed not that long afterwards. And the evidence for this comes in the form of little zircon grains. Detrital means that they are just part of the sand. They're chunks and pieces. And you notice that most of these still have something of a crystalline shape. And zircon is very durable, both chemically and physically. It's a hard mineral, and in terms of just how strong it is, and it's chemically very strong as well. And so it lasts and persists and gets recycled in the sediments and reworked from one formation to another formation. And some of it goes back a long way. It contains uranium, and because of that, they could date some of these, and they dated back to about 4.2 billion years. So that's getting way back. And it has oxygen, which indicates there was free oxygen available at that time on the planet. So they were dated back to 4.3 billion years, and that is pretty early in the history of the Earth's development. And to have free oxygen then is kind of remarkable. But that oxygen that they do have has a high level of oxygen 18. And oxygen 18 is an isotope of oxygen that is a bit heavier than the standard oxygen 16, which most oxygen is. And because of that, because it's a bit heavier, the degree in which it's concentrated in a liquid depends on the temperature. And when it's cold, there's less water vapor, less of it can escape into the atmosphere, so it gets concentrated in the water. So the waters are enriched in oxygen 18 if it's cold. And this is used as a geological thermometer for identifying the water temperatures during the glacial and interglacial intervals of the ocean as we move into the Pleistocene. So a high level of oxygen 18 suggests a somewhat cooler climate. And that runs sort of counter to a lot of the other thinking about the character of that early Earth. But there's another factor, and that is that the sun has been getting brighter since its original formation. And about 4 billion years ago, it was only about 70% as bright as it is today. And what this means is that as you look at the amount of incoming radiation and getting back to 4 billion years, there is less solar radiation reception. The blue line is the radiation reception today in kilowatt hours per meter squared per day. And it's high at the equator and gets progressively lower as you get up to the northern latitudes, because as you move away from the equator, the Earth's surface slopes increasingly away from the sun. And so that radiation is spread over a wider and wider area. So if we project back into the past 4 billion years ago, the red line, and look where Monterey is today, we would be getting far less radiation from the sun than we do at the present time. In fact, that amount of radiation that we would have gotten at that time is about the same as today is received at the southern end of the Arctic Circle. So solar radiation was lower, and the Earth, that would have had a really cooling factor on the Earth. At the same time, though, there were lots of greenhouse gases. So we just don't really know that much about the Earth's early history, but the solar output was low. It was a greenhouse gas atmosphere, and were the global temperatures too hot for liquid water, or could it have existed from time to time? As we go a little bit later and get into about 3.8 billion years, we get into a time when comets and a lot of bombardment was coming in from outer space. And this could have added more water to the Earth. It's called the late heavy bombardment. It's based upon the amount of craters that have been found and their age on the moon. And presumably the Earth took the same kind of a beating about 3.8, 3.9 billion years ago. And those comets would have added water. So water probably was being added over a fairly long period of time. The National Oceanographic Service says liquid water could exist after about 3.8 billion years, but it might have existed even before that. Whenever it was, it cooled enough that clouds formed, and it started to rain, and it rained, and it rained, and it rained. And puddles became pools, and pools became ponds, and ponds became lakes, and lakes became seas. And we have the first standing bodies of water on the planet in those early days. Now, today, we live in a world of oceans and continents, and they're not dependent upon water. If we didn't have any water on the planet, I think we'd still have basins like this and continents just from plate tectonics. So the Earth has two kinds of crusts, oceanic crust and continental crust, and the oceanic crust underlies the ocean basins. The continental crust underlies the continents. And that really establishes the ocean and continental configuration of the Earth. So the oceanic crust has got heavy elements like iron, calcium, magnesium, and it's typically dense and dark. The crust of the Hawaiian Islands is a good example. And continental crust has got lighter elements, silicon, aluminum, potassium, sodium. And it forms things like the Sierra Nevada. So where did continental crust come from? It probably all started as pretty much an oceanic type of crust. And the idea is that, I think the best idea is that these early magmas, as they cooled, the minerals that and elements that had the highest melting point came out first and accumulated on the bottom. So what you got was a removal of the iron and the calcium and the magnesium with time. And eventually what you're left with is a magma that's enriched in aluminum, silica, and the lighter elements. And so very likely that happened early in the history of the Earth. So the heaviest minerals was iron, calcium, magnesium settling out first, and then finally leaving behind a magma that would be the material that would, when it crystallized, that of the continental crust. And so 3.7 billion years ago, we very likely had continents and oceans. The continents would have been smaller if these earliest plate tectonics, and the oceans would have been a lot shallower than they are today, but they would have still been there. And that set the stage for a catastrophic change in the Earth. We noted that the water molecule is kind of strange in that the charges are not symmetrically arrayed. And because of this, it can incorporate a lot of ions in solution. So it's a very solvent. It's almost, some called it the closest thing we'll ever have to a universal solvent. But lots of different elements can mix with the water. And some of these come together to form some fairly complex organic cells, including carbon and oxygen. And some of these complex organic cells began to replicate themselves. And when they did, life arrived on planet Earth. And so when was the earliest life? Well, it's hard to tell for sure, but probably it existed before 3.5 billion years. And the reason I say that is that the early rocks have some very strange features in them. These features are called stromatolites. And they puzzled geologists for decades until they were found in modern bay, and a modern bay on the west coast of Australia, northwest coast, Sharks Bay. And they're essentially mounds made up by blue-green algae or blue-green bacteria, cyanobacteria. And these are probably the oldest fossils that have been found on Earth, dated at 3.5 billion years from Western Australia. And you can see there is a very strong similarity to the structure of a stromatolite in this formation in Western Australia. And this is generally recognized as the earliest indication of life on the planet. These cyanobacteria that form the stromatolites are pretty darn amazing. They're kind of the Swiss Army knives of bacteria. They can survive long episodes of desiccation, low salinity, intense ultraviolet light, and extreme temperatures. So they can live in a lot of different places. And not only that, they made their own food by photosynthesis. And photosynthesis, just to remind everybody, is the process where, using the energy from the sun, carbon dioxide and water becomes converted to sugar and oxygen. So the Earth's early atmosphere didn't have any oxygen, probably mostly nitrogen, water vapor, carbon dioxide, maybe a lot of methane. And the ocean 3 billion years ago had a lot of dissolved iron. The ocean might have looked greenish. But these cyanobacteria were producing free oxygen. They were, as they photosynthesized, oxygen started to build up, first in the oceans, and then escaping into the atmosphere. So that about 2.5 billion years ago, there were starting to be some major changes. And all that dissolved iron in the ocean starts to oxidize, essentially rust, as it comes in contact with the oxygen. And I know a little bit about this because about the consequences of oxidizing iron, because I grew up in this house, this northeastern Ohio. This is where I spent my grade school years. We had a little creek along the house, but we had a water well that was really pretty nasty. It dried up in the summertime, and it was quite unreliable. So my father had a new well drilled, and it went down about 100, 118 feet, as I recall, and it hit water, but the water didn't stay down there. It came up to the surface. It was an artesian well because there was pressure on that water that drove it up to the surface. I remember it as the best tasting water I ever had in my life. And maybe the reason it tasted so good was it was full of iron. Now, the water itself was absolutely clear, but once it came in contact with air, it rusted. This is another well of similar character, but a lot of iron. And we had the same thing. We had iron stains all over the driveway. In fact, the water was basically useless. It was a household water, despite how good it tasted. And so this happened in the oceans as oxygen came in contact with the iron. And we went from a world without oxygen to free oxygen in the atmosphere, and particularly in the oceans. The dissolved iron precipitated out and formed thick accumulations on the seafloor. And most of the iron that we mine today comes from that particular period of time. The great iron mines of Minnesota are all derived from this particular period. So the next time you pick up something made of steel, like a knife or any other utensil, you might think a moment about the origin of the iron that's in there, that goes back to a catastrophe that happened about 2 to 2.5 billion years ago. Because it was a catastrophe, the oxygen was toxic to almost everything else that lived on the planet at the time. So it almost killed everything else off. And the cyanobacteria, those survive. They still survive today. If you go to Point Lobos and look at that, the sort of darkish area just above the water line, that's cyanobacteria that's causing that color change. But that is not where most of the cyanobacteria are. The chloroplasts in plants today that allow them to photosynthesize are basically cyanobacteria. So as you look out the window and see the green leaves, what you're seeing is a world of cyanobacteria. They are truly remarkable organisms that have changed the world in so many different ways. So the other thing that happened is oxygen got into the atmosphere. It started replacing carbon dioxide and methane, the greenhouse gases. And as a consequence, the rocks that were deposited at that time show evidence of glaciation, like drop stones, where rocks fell from icebergs into the sea and are just isolated big chunks in the muddy sand of the ocean floor, or big bulldozed masses of mixed up rock like the one on the right-hand side. So this is the first really widespread ice on the surface of the planet comes at that time. And then following that, we go into a remarkably long period, about 1.5 billion years, where there's not a whole lot of change. As far as we know, organisms didn't change that much, and there were no major events that happened on the surface of the Earth until about 600 to 700 million years ago, when the Earth again went through a glacial phase, which we don't understand. But again, much of the Earth's water was turned to ice. Well, let's talk a little bit about the salt of the oceans. Where did all the salt come from? About 38.5 quadrillion tons of salt are thought to be in the ocean. Where did all that come from? Well, not like this, but it is commonly said that rocks on land are the major source of salts dissolved in seawater. USGS, salt in the ocean comes from the rocks on land. The idea is that weathering of the rocks releases the elements, puts them in solution, and they go down and collect in the ocean. And that's sort of a common wisdom, and I think it's inaccurate. And the reason I think it's inaccurate is that sodium is a common element in rock-forming minerals, but chlorine is not. And it is hard to see where all that chlorine comes from. And probably the best guesses, I think, are that they may be the result of outgassing on the early Earth, put chlorine into the atmosphere that eventually found its way into the ocean and merged with salt and formed the present day salinity. Well, chlorine, if you have a swimming pool, you know that you put chlorine to keep the algae down. And we don't know that that's this long period of time where things didn't change that much, how much chlorine might have been in the ocean. But a thought I had as I put this together is that it's conceivable that maybe there was enough chlorine in the ocean water before it connected with the salt, with the sodium to form salt, that it actually inhibited the development of new organisms. Don't know, probably not. I think the best statement I read on the origin of the salt in the oceans came from a book on the geologic history of seawater. Our knowledge of ancient oceans is minuscule compared to our knowledge of the modern ocean. Even the course of the major element concentration in Phanerozoic, which is a time since the last 500 million years, seawater is still rather poorly defined, and estimates of their concentration in the Precambrian seawater, the long period of time that went before that, are a little more than guesswork. And I think that's kind of where I have to leave it today. Sea level is of fundamental importance to geology, particularly the geology of working the coasts. And sea level, as we noted last week, can be the result of sea level change, can be the result of two things: an absolute change, which is in the water level itself, or the crust can move up and down. And as it moves up and down, the sea can move in or out depending on how the crust is moving. So we have these two different approaches to changing sea level at any one area along the coast. A variety of durations and causes for sea level change. And if you go to the really long periods, tens of millions of years of change, that has to be due to plate tectonics. Back in the 1980s, geologists at Exxon Production Research came up with a sea level curve through the Phanerozoic, the last 500 million years or so of geologic time. And this is a very strange looking curve, but they really believed it. I know because when I was with Conoco, I was with part of a group that was designed to try to implement what was being learned about sea level change, to apply that to the understanding of the rocks that our explorers were working on. Some of the older members of the Exxon production research team retired and went into working as consultants, and we hired a couple of them. And I watched them work, and the way they did it was they would sit down and put down the curve. And once they got the curve down, then they'd find out what was going on from the curve, and then they'd start interpreting how everything fit. And this didn't strike me as particularly good approach, unless you really believed in that curve, which I had some skepticism toward. And then I was given a project in Indonesia where I was looking at some rocks that had been studied before. And unlike most places, there was really good paleontologic data, which meant that you could get the ages quite well. And there were lots of cores, which meant I could interpret the sea level change. And so I put together my own sea level curve for this particular period of time, which was right around the 200 million, just before the 200 million mark. And I thought, now I'll compare the two curves. Once I've got my curve, I'll compare the two curve and see how far off the Exxon curve is. And I put them together, and it was a 1-to-1 match. I was just astonished. And it gave me a lot more faith in the curve, although I still would not start with it as the primary premise. But there are some really major changes in here. And what would cause those changes? Well, about the only thing you could do to change that would be to change the shape of the basin, because the water volume has to stay pretty much the same. But if you're pushing up from the bottom, sea level will rise, and increased subsea volcanism will cause the sea level to rise. And so that is one of the explanations for the rises of sea level. But we also have some falls, and particularly the fall around 300 to 325 million years is a remarkable drop in sea level. And another way you can change sea level and get it to fall is to widen the basin. So if you take a tumbler of glass, water stands up so high, but if you put it in a pipe pan, same amount of water stands much lower. And so as the basin width expands, the water level falls. So can you do that geologically? Well, what was going on in plate tectonics at that time were the continents were merging, crushing together. And in that crushing together, they would have reduced, they would have been compacted together. So that meant there would be more surface area in the oceans. And so that would be one way of causing such a marked decline in sea level. The other thing that would happen as a consequence of that is you would get more surface area that would be covered by the sea, and it doesn't reflect heat nearly as well as the land does. So you might expect it to get colder. And if you look down at the bottom of the diagram, there are extensive glaciers that are known to have occurred at this time. So that can give us some explanations then for this rather remarkable curve that shows really some pretty drastic changes in sea level, although they occur over long, long periods of time. Going to shorter periods of time, we have glaciation. We talked a bit about that last week when the glacial changes in sea level being high during the warm periods and low when the glaciers existed during the ice ages, because that would have taken water out of the ocean and stored it on land. Glaciers covered much of North America and Eurasia at the time. That water had to come from somewhere, and it came from the sea. And so sea level dropped about 100 meters or so every time we went into a glacial episode. There's still a lot of ice on Antarctica, about 2.5 miles over much of it. That ice is melting today. And this is a point of concern. If it all melted, the coast of the United States would look very, very different. And many, perhaps most of our coastal cities would be well underwater. And it happened about 50 million years ago. This is a reconstruction of what the world might have looked like 50 million years ago. And again, you can see most of the coastal areas that are occupied today are flooded at that time. At a much smaller scale, a decadal scale, we could get changes in sea level just from sea temperature changes. If you have a cylinder of water and you put heat on one side and ice on the other, it's going to expand and rise where the heat is and contract and sink where the ice is. And so there have been changes that have mapped. They're not great changes, about 7 centimeters of change, rise or fall. But if you live on an island like Majuro, the Marshall Islands, where there's no real protection from the waves, a very small rise in sea level could seriously increase the amount of coastal erosion and cause some real damaging problems for the people who live on islands like this. And then also at a decadal scale, we have coastal subsidence. And this is a relative sea level change. This comes from the land sinking. And it's most common where there are river deltas, where rivers build out large plumes of sediment or masses of sediment into the adjacent body of water. And a huge number of people live on deltas today. They're flat, there's plenty of fresh water, it's not a limiting factor. There are harbors, natural seaports, and so there are just an awful lot of folks that live there. And deltas naturally sink under their own weight. And so that with time, it would go from this to perhaps even complete inundation. The Mississippi Delta is sinking at a rate of about 12 millimeters per year in some of the most extreme areas, but that's would be perhaps a matter of a foot or so in a decade or two. So it would be a significant drop in, or relative rise in sea level. And it can be impacted by human activity. Just the weight of the structures that are put on the deltas cause them to subside, or pumping out the groundwater. And this happened in Tokyo, a drop of about 4 meters that was caused by extraction of groundwater. And once the groundwater is pulled out, the sediment compacts, and they managed to stop it in 1975, but there's no recovery. It still is going to be about 4 meters below sea level relative to where it was at the beginning of the 19th century. About 500 million people live in delta regions that are threatened by subsidence, and they're also threatened by something else. And that is the sea level change that occurs on a level of days and is weather related, and it's an absolute change. This is caused by storms that push large volumes of water toward the shore where they pile up and flood the coastal regions. And these can be significant tides, storm tides, superimposed on a normal high tide, can flood a lot of area and create a lot of damage. So the storm surges can be really very, very nasty. And the size of the storm power, is strongly connected to the sea surface temperature. And as a result, storms are going to get stronger because the ocean heat is unquestionably increasing. And so the storms form in the tropical regions. And one of the things I did was to look at the magnitude 5 hurricanes over from the period of 1920 to 2020, 100-year period. And 13 of them occurred in the first 80 years and 13 in the last 20. So big storms are becoming more prevalent. In this study, they looked at what they said were the strongest hurricanes and typhoons since 1979. There are 7 of them, and 5 of them were in the last decade. So there's little question that the storms are getting much bigger and stronger. Flooding from high tides in the US has doubled in just 30 years. 50% of New York City is considered to be at risk. And to protect the city, it's going to cost about $4 billion. And this was a few years ago. It's probably gone up since that time. A city like Miami, it's been questioned as to whether the city can be saved economically, whether it's worth trying to preserve it or whether they're just going to have to let it go. So it's a serious issue. The economic losses in just this century from hurricanes has been about $500 billion. And Asia is where the brunt of the problem is going to, I think, really hit, because there are about 500 million people that live less than 30 feet above sea level. This is called the low elevation coastal zone, the LECZ, and the number of people who live in that zone by country is phenomenal, um, well more than the population of the United States. And storms, particularly the flooding associated with storms, is just devastating in terms of the numbers of deaths. This is looking at reported deaths due to tropical cyclones in the period 1970 to 2012. And there are hundreds of thousands of people that have been killed and many, many more lives disrupted and changed as a consequence. So water can be a scourge, but also a vital resource. And we'll look a bit at the hydrologic cycle because this really determines how much water we get. So water evaporates, goes into the atmosphere, comes up from plants, then comes back to the earth in rain and snowfall. That supports the plant growth. It infiltrates into the ground and floods back into the ocean, and the cycle just repeats itself. And disruptions of this cycle are what give us problems because the water cycle does not stay in balance. There are floods and there are droughts. Many places have either too much water or not enough. And the droughts have killed an awful lot of people. They are probably one of the more dangerous things that happens to humans on the planet. And we're in a drought here, as probably everybody knows. Study of tree rings indicated this is the driest 2 decades in the last 1,200 years. But be careful what you ask for, because this is a journal of a man named William Brewer, who was part of a survey team, a geological survey team, looking at California resources in the 1860s. And he kept a journal that was remarkably well written. And Sunday, January 19th, 1862, the rains continue, and since I last wrote, the floods have been far worse than before. Sacramento and many other towns and cities have again been overflowed, and after the waters abated somewhat, they're up again. That doomed city is in all probability underwater today. The amount of rain that's fallen is unprecedented in the history of the state. This year in Sonora and Tuolumne County, between November 11th, 1861 and January 14th, 1862, 72 inches at 6 feet of water has fallen, and in places, numbers of places over 5 feet in a period of 2 months. February 9th, he wrote, nearly every house, referring to the Sacramento-San Joaquin Valley, nearly every house and farm over this immense region is gone. There was such a body of water, 250 to 300 miles long and 20 to 60 miles wide, the water ice cold and muddy, that the winds made high waves that beat the farm homes in pieces. And something like that today would just be unthinkable. Well, the last thing we'll talk about is water here and now. And the part of it we'll focus on is the infiltration part, where the water sinks into the ground. There's not that much fresh water. It's groundwater, which is where most of the fresh water is less than 1% of the total water on the planet. And this shows the relative amounts of liquid fresh water on the surface and freshwater lakes and rivers. They're really relatively small. And the water exists in aquifers, groundwater, and the unconfined ones feed back into the surface and feed the streams. But there can also be the confined aquifers, like the one that was hit The drilling of that well alongside the house in Ohio, hitting aquifers that are stuck down there, buried and confined, but can be tapped by a well. Our water resources here in Monterey have been two sources, two aquifers, one in the Carmel River Valley and the other just up to the north towards Seaside. And it looks like we're going to have to rely on the one at Seaside for our water in the future. Subsidence is an issue because when water is pulled out of the ground, particularly the fine grained silt and clay, loses its space, the pore space, and it collapses. And so the ground actually sinks. And the amount of sinking has been phenomenal in the Central Valley. This is 4.8 feet, nearly 5 feet in 25 years. And this is, I'm not sure quite where this is, but in the period between 1925 and 1977, there has been that much sinking of the land. And that's in part loss of reservoir. Our reservoirs here are close to the sea, which is, for many places, another problem, and that's saltwater intrusion. A water well draws the water down as it's pumped out, but it also can pull it up. If a well goes down and encounters the salty water that's coming in the subsurface from the ocean, it'll draw that up into the well and pull it up. And so the pumped well becomes salty, and that is the saltwater intrusion. And this shows the saltwater intrusion for the lower Salinas River over the recent half century or so. And you can see there's been a significant increase. It's reduced. They've actually started about this century, they've reduced the rate of saltwater intrusion, but it was pretty severe for a while. So that is pretty much the story on water. And so we've reached the end.